This diagram represents part of an electric circuit. All resistors are identical. We've got V1 and V2, and they're showing separate voltmeters. When current flows in the circuit, which one of the following represents the relationship between the two voltmeters? Now, with all of these multiple choices on electricity, you need to think quite carefully. We've got one resistor in series here. Let's just pretend, for argument's sake, we can't use 2. 2 turns out funny. But let's go with 3, 3, and 3. This is going to have 3 ohms of resistance. This, when you work it all out, is going to land up being 1,5 ohms of resistance. So the voltmeter reading, if the voltmeter reading on V2 is X, I'm going to need double the amount of energy per coulomb of charge to be able to move through the bigger resistance. So in other words, what can I say? I can say that V1 is twice the value of V2. A teacher supplies the circuit diagram 1 to her students. The students have set up the circuit, but the one group of students set up the circuit as illustrated below. Which of the tables give a reading? Now, firstly, voltmeters have got exceptionally high resistance, but they can let current go through them if there's no choice. So that's going to be a very high, big resistor. And then here, the current, the ammeter, is going to have all of the current flow through there. So what you're going to land up with is a situation where the ammeter reading, the voltmeter has no difference in energy whatsoever between the 2 points because it's just sitting here on the series branch. So the voltmeter is going to land up reading 0. And then what's going to happen is my ammeter, has very low resistance, so none of the current is going to go through that resistor. All of the current is going to go through that ammeter, so that will end up being a large reading. The resistance of the battery and the ammeter is given as negligible. The 2 resistors in the circuit are identical. As soon as I close that switch over there, what is going to happen is I am going to land up with half of the resistance, okay, of what I used to have, and therefore I'm going to land up with double the current. Again, might be handy to stick some numbers in over here. So I started off with 3, and let's just pretend this is a 12 volt battery. So 12 divided by 3 is going to land up being 4 amps. Now I'm going to go 12 divided by, this reduces to 1,5. 12 divided by 1,5, and I am going to land up with 8 amps. So I have got double the current reading. 3 identical cells have the same EMF and the same internal resistance. They are in parallel to form a battery. What is correct? The EMF is going to be in parallel. Remember, you get the same energy as if you were connected in series. You don't get any more, they just last longer. So we are going to land up with exactly the same E value. And then you are going to say, what is going to happen to the resistance? Well, my resistance is going to reduce, and it's going to reduce by 1/3 because I now have 3 parallel branches. You've got a diagram here. There's no internal resistance again, and the meters don't interfere. The resistance of R does not change with an increase in temperature. How do the readings of the ammeter and the voltmeter change when I put another resistor in parallel? When I put another resistor in parallel, I now am going to decrease the amount of resistance, and therefore I will increase my current reading. Also, my voltmeter, because there's no internal resistance, there's only one place for this. If it had 12 volts on the outside, let's do some colors and see this. Oopsie, sorry. It doesn't really matter. The voltmeter is still reading across the terminals of a cell that doesn't have internal resistance. So the voltmeter is going to remain unchanged. So C is my correct answer. I've now got X and Y. They're connected in parallel to a negligible internal resistance battery. Again, if the resistance of X is less than Y, then the current and power in X are going to be. So I've got less resistance. I am therefore going to have, let's say this is 3 and this is 6. If I landed up having 2 amps going on that branch, I would have 1 amp going on that branch. So the current in X is going to be greater. What about the power in X? Well, power is going to be equal to V times I. I will have the exact same voltmeter reading across both of those. So I land up with V and I will have that the power, if I've got more current, will be greater as well. My voltmeter is the same, so if the current goes up, the power must go up as well. We've got an ohmic resistor, and it is connected in series to a power source and a rheostat. The potential difference across the resistor is gradually increased. Which of the graphs best represents the relationship between power and potential difference of a resistor? So I look at an equation that links all of those things to me. The resistor will stay the same. There is now a relationship that has been established between power and potential difference, and it is a squared relationship. In other words, the power increases to the square of the V, which kind of looks a little bit like y is equal to x squared, or half of it, which is a bit of a parabola. So A is going to be your correct answer. That is a exponential relationship. A length of resistance wire has a resistance of X. If the wire is bent in half, so it was X altogether, now I bend it in half, it is X, half of X, and half of X. So those are twisted together and connected to the circuit. So now we've got, in essence, a parallel network. Half of X and half of X, if I work out the effective resistance, is going to land up being a quarter of X. So you now land up with a quarter of X altogether as the effective resistance of that setup.